Hi, my name is Silvana Aristizabal, and this is my lab report for Lab 1 on constant velocity. Here's the table of contents of what we're going through in this presentation. Firstly, the introduction. The overall purpose of this assignment is to observe, analyze, and model the motion of an object moving at a constant speed without changing direction. We will achieve this using three main tools: Tracker for video analysis, GlowScript for building the computational model, and spreadsheets for comparing the observed position of the object from the video analysis with the predicted position from the computational model and seeing how they differ. All of this helps us gain a deeper understanding on Newton's second law of motion. So let's explore more about this fundamental principle. The momentum principle states that the net force acting on an object is equal to the rate of change of its momentum over time. In other words, when a force is applied to an object, it changes its momentum, which is the product of its mass and velocity. We can see here how by deriving from the momentum principle we can obtain the velocity update formula, which allows us to determine the object's velocity at each time step when dealing with a non-constant force. Once we have the updated velocity, we can use it in the position update formula to predict the object's future position over time. Overall, this principle helps us understand why objects speed up, slow down, or change direction depending on the forces acting on them. Now that we understand this principle, let's see how we can apply it to our lab. First, recorded a video of a marker rolling on a table and uploaded it to Tracker to record position at each timestamp. Then, based on the position, velocity, and time gathered from the video analysis, we created a computational model of the marker's position on GlowScript. After that, we grabbed the position versus time results from both the computational model and the video analysis. Finally, we compared results and analyzed the difference between the data obtained. Now, let's take a look at the actual motion we analyzed. Here's a video of the marker rolling, which we use for our video tracking. By examining its motion, frame by frame, at each of the red diamonds, we collected position data. With this data, we were then able to construct a computational model of the motion we observed. So, from our data, we know the starting and final time and position. We use this to calculate velocity using this formula. Additionally, we can also find the changing time, which is the time between each of the data points recorded. We then plugged in initial position, calculated velocity, initial time, change in time, and final time. Then we applied Newton's second law here and set the net force to 0. By running this code, we got a series of numbers that indicated the position of the center of the mass at each timestamp according to the ideal modeling of the motion we observed. If we graph these computational results side by side with the actual observed results from the video analysis, we obtain a graph that looks somewhat like this. As we can see, the orange dots represent the computational model results, while the blue dots represent the video analysis position. While the computational model generally follows the video analysis data, there are slight variations, particularly at later time intervals. These deviations and somewhat curved trajectory of the video analysis data results from factors like friction that were not accounted for in the model. More clearly, our system, the rolling marker, is influenced by its surroundings, including friction and air resistance, explaining the small deviations between the computational model and the observed motion. Now, let's take a closer look at the possible sources of error in our experiment and how they might have affected our results. First, human error when conducting video analysis, given that we had to manually input the position at each timestamp, then rounding errors that could have affected our calculations, camera angle misalignment when we initially recorded the video, and dismissing external environmental factors. So now let's reflect on the overall experiment by answering these questions. So what were to happen if we flip the axis? The motion of the marker will be mirrored across the y-axis given that the position plotted in the positive x will now be plotted in the negative x. Thus, the slope will be negative, thus the velocity will be in the negative direction. However, speed or the magnitude of the velocity will remain the same. Does the net force equal 0? Is it possible to say how many forces are being added together to give 0 net force? So the curvature tendency observed in the video analysis suggests that the net force is not 0 and the object is experiencing acceleration, thus not a constant velocity. For the net force to be 0, all acting forces must be balanced. However, it is impossible to say how many forces are being added together to give this 0 net force. Thank you so much.